we're going to talk now about hydrolysis of salts. And so in particular, these are salts that affect pH. So these problems are kind of challenging because they require both a lot of conceptual thought plus the calculations. So we're going to go through both parts of this. So our problem is a 0.215 molar solution of lithium fluoride is prepared at 25 degrees C. Lithium fluoride is formed by the reaction of the weak acid, hydrofluoric acid, and the strong base, lithium hydroxide. The value of Ka for hydrofluoric acid is 3.5 times 10 to the negative 4. So what is the pH of the solution? So that's what we're looking for. Now, this particular problem does tell us where our salt came from, but we would be able to figure that out even if we weren't told that. So let's go ahead and just write down the two components of our salt. And basically, when you see fluoride anion, you're going to be thinking about hydrofluoric acid. And when you see a cation, you're going to be thinking about hydroxide very often. Okay. And so remember that lithium hydroxide is one of the strong bases that we have to memorize on the list that we have for both Chem 111 and Chem 112. Now, hydrofluoric acid is actually a weak acid. It's not on the strong acid, strong base list. And the other reason that we know that is that we were given a Ka for it. And like, let's say that it didn't tell us this part. Let's say that it didn't tell us it was for hydrogen fluoride. We should still be able to figure that out. Okay, so let's go ahead and begin solving this problem. Now that we know what our salt is, and we know the two components, and we know that lithium is the conjugate acid for a strong base, and remember the conjugate seesaw, the stronger the base, the weaker the conjugate acids. So that means this guy is super weak, which means he's not going to affect the pH of water. It's the reason why you don't think of lithium cation affecting the pH. You don't think of sodium cation affecting the pH. So if this was sodium hydroxide and sodium fluoride in water, but when we see the conjugate base of a weak acid, so the stronger the acid, the weaker the conjugate base, or the weaker the acid, the stronger the conjugate base. So we know that this anion, this fluoride anion, will affect pH. All right. So that means that is our active species in water. So let's go ahead and write down the solution that we would get when we dissolve lithium fluoride in water. Now I'm going to leave the lithium cation out of the equation because it's just a spectator. It doesn't affect the pH. So let's simplify life for ourselves and just leave it out. Okay, so we're going to dissolve fluoride anion in water. And we're going to get the conjugate acid, which is hydrofluoric acid, and hydroxide. So we are making a basic solution. Now, one thing that we want to think about, we're making a basic solution and we were given a Ka. So I'm going to write that down. We are making a basic solution and we were given Ka. We need Kb, okay, because we have a hydroxide concentration. So we're going to have to calculate KB before we can really do anything else. So let's go ahead and do that. Remind ourselves how to do that. So let's calculate KB. So we take KW is equal to KA divided by KB. And now when we solve for KB, we're going to have KW divided by KA. Going to plug in the constant. Okay. And it's 1.0 times 10 to the negative 14 at 25 degrees C. So now you know why they gave us that. Otherwise, we don't really need it. And then 3.5 times 10 to the negative 4, because we were given that Ka value. And we can calculate KB as 2.857 times 10 to the negative 11. All right, so that's good. So now we have KB. Good to go there. So I'm going to go to the next slide, and then I'm going to rewrite our equation, and we're going to start setting up the ice table so that we can figure out our equilibrium constant expression. So let's rewrite our reaction here. Okay, so there's our expression. And let's go ahead and set up our ice table now. So we have initial, change, and equilibrium. Now, initially, it gave us a concentration of 0.215 molar of the lithium fluoride, which means that we have 0.215 molar fluoride anion and 0.215 molar lithium plus that we don't care about. Okay. That's a spectator. So we don't care about that. So all we need is our concentration of our fluoride anion, which is the same as the concentration of the salt. Now, remember, water is a pure liquid, so it's not going to affect the equilibrium constant expression. The activity is 1. So I'm just going to leave that alone, skip it, and go over and figure out what our initial concentrations would be if we put this salt in water. And so we're assuming that this is before anything happens. So the very, very split nanosecond, right when you put it in there, nothing has happened. No dissolution has happened. No reaction with water has happened. And so that means that that initial concentration is 0. Now, at equilibrium, you have to have some of everything. So we have to figure out which way this reaction is going to shift to reach equilibrium. And since we have 0 on the product side, that means that we have to have something. It has to shift toward the products so that we have something of everything at equilibrium. And it's going to have to come from those reactants, which is the fluoride anion. Okay, so now we have the directions for the equilibrium. And now all we have to do is sum each one of these. And this would be 0 plus x. So I'm just going to write x, 0 plus x, going to write x. Okay. And now we're going to go ahead and set up our expression. So remember, we need KB. So I'm going to write that so we don't forget. And let's write our value, 2.857 times 10 to the negative 11. And then our expression, remember, it's products over reactants. So it's going to be the concentration of HF, concentration of hydroxide, concentration of fluoride anion. Okay. And now let's go ahead and put in our values from our ice table. And we end up here. Okay. So now let's go ahead and do the math. So we have 2.857 times 10 to the negative 11 equals x squared over 0.215 minus x. Now remember, we can do a simplification because we have a very small exponent, and that means x is going to be negligible. So we can assume that it's 0. Okay. So after we do that, now we have easier math. 2.857 times 10 to the negative 11 is equal to x squared over 0.215 0.215. Let's multiply both sides by 0.215. So now we end up with 0.215 times 2.857 times 10 to the negative 11 equals x squared. Let's do that multiplication. And so we're going to end up with 6.1426 times 10 to the negative 12 equals x squared. Take the square root of both sides. And we end up with x equals 2.478 times 10 to the negative 6. All right. So now we know our x. So what does that x mean? So now we have to look at that. So let's go up to our table and we can see that the hydroxide ion concentration is x. So this is the concentration of hydroxide. All right. So that's super handy, because we can use that to calculate the pOH. Now, if you calculated the pH with this concentration, you will get the wrong answer, because what you're actually calculating is the pOH, because that's what we have in solution. So calculate pOH, negative log of the concentration of hydroxide. So pOH is equal to negative log 2.478 times 10 to the negative 6 equals 5.61. So there's our pOH. Now we have to calculate our pH. Okay, so let's go up here. pH is equal to 14 minus pOH. And it's 14 at 25 degrees C, which we are at. And so all we have to do is plug in, and we end up with 8.39 as our pH. All right, so let's just think about this for just a second before we move along. And let's go up to our equation. So we have fluoride anion, which is a conjugate base, put it in water, produces hydroxide. So we should have a basic solution. We look at our pH and it is 8.39, which is basic, right? It's a pH that's above 7. Here's another way you can catch yourself with pOH. Notice it's 5.61. If that was the pH, that would be an acidic solution because it's less than 7. So that also tells us that we haven't quite gone far enough and that we have the wrong answer. So the pH should be in the basic range with this salt, and it is. So we are good to go.